Very well. So the question says, find the rate of change of the function in the direction of u equals to cosine pi over 6 and sine pi over 6 at point 1 and 2. Well, we know that the directional derivative of function f in the direction of u at point x sub 0, y sub 0 is given as f of x, partial derivative of f with respect to x. It means that you are taking the directional derivative of the function along with x-axis and evaluate that at point 1 and 2 times cosine pi over 6 plus. Now we have to work with the rate of change of the function in the direction of y-axis at this point, f of y, 1 and 2, times sine pi over 6. Very well, so we need partial derivative of f with respect to x. Partial derivative of f with respect to x is going to be, let me write it here for you, f of x is 3x squared minus 3y, and f of x at 1 and 2, it means that your x is 1, your y is 2. We get 3 times 1 squared minus 3 times 2, which is 3 minus 6, negative 3. And then partial derivative of f with respect to y is equal to, so this side is going to be 0, this is going to be negative 3x plus 8y. Now we're going to find the rate of change of the function in the direction of y-axis at point 1 and 2. So f of y evaluated at 1 and 2, which is equal to negative 3 times 1 plus 8 times 2, negative 3, 16, which is positive 13. So here we get positive 13. Okay, you have cosine of pi over 6, which is square root of 3 over 2, and you have sine of pi over 6, which is a half. So, and here we have plus. So to calculate the exact value, we need to have a calculator. So you get 13 over 2 minus 3 square root of 2 over 2.
Sure.
Okay, guys, this is 3, not 2. Thank you, Bernice. So, to calculate the directional derivative of function f in the direction of u at the point x sub 0, y sub 0, we have 3 options. We have 3 options. The first option is using the limit definition. Option 1, limit definition. This is your very first choice. If you're not sure if the function is differentiable or not, you have to use the limit definition. Option 2 is when you know that the function is differentiable, so you can use a shortcut. If you know that your function f of x and y is differentiable at the point x sub 0, y sub 0, then of course you can say that, hey, the derivative of the function, the directional derivative of the function in the direction of u is equal to, I take the partial derivative of f with respect to x, evaluate that at point x sub 0, y sub 0, multiply that by a plus the partial derivative of f with respect to y, evaluate that at point x sub 0, y sub 0 times b. What is a? What is b? Those are the coordinates of your u. Okay. Option 3. If, again, you are sure that your function is differentiable, then the directional derivative of function at points x sub 0, y sub 0 in the direction of u is equal to. So f of x, again, evaluate at x sub 0, y sub 0 times cosine theta plus the directional derivative of f with respect to vertical line, vertical axis at point x sub 0, y sub 0 times sine theta. What is cosine theta? What is sine theta? Those are polar formats of u using theta. Note that since it's a unit vector, r is equal to 1. If you're wondering where is r is equal to 1 because it's a unit vector, unit circle. So here you go. In both cases, you have to make sure your function is actually a differentiable function. Let me just project this for you here on the note. So in this question, it says, use the weather map in figure on the left-hand side to estimate the value of the directional derivative of the temperature function. So suppose you have a temperature function like T at Reno. So here you have Reno, which is the point x sub 0, y sub 0. It's just a location. Reno as a city. It has a location. So it has x coordinate, y coordinate, z coordinate in the southeasterly direction. So the direction towards southeast. How do we approximate the directional derivative? What is the derivative? The directional derivative is actually gives you the rate of change. The rate of change. In the temperature, you see two changes in the direction here between these two. We're not looking at the Las Vegas temperature. We're not looking at the Los Angeles temperature. We're not looking at temperature around San Francisco. We want to know the rate of change, of the temperature in the direction of southeast. Well, on the numerator, you have to find the difference between these two temperatures. 60 minus 50 divided by 75 miles. So by doing the calculation, you get almost 0.13 degrees Fahrenheit per mile. Rate of change of the temperature. Very well, so let's talk about gradient of a function. So where are we? We are on page 3. Page 3, the gradient of a function. So far we talked about directional derivative, which is just a fixed number. Now we're going to talk about a vector function, which is gradient function. So suppose you have a function in two variables. Let f of x and y be a function in two variables. The gradient of the function denoted by gradient of f, not log f, is defined as f of x in the direction of x-axis plus f of y in the direction of y-axis. Note that this is a vector function, so you can define the gradient of the function as a vector f of x, comma, f of y. A vector function with two coordinates, f of x, partial derivative of f with respect to x, and partial derivative of f with respect to y. Well, what is the connection between gradient of a function and the directional derivative? So note that for function f of x and y, the gradient of the function is defined as f of x, partial derivative of f with respect to x in the direction of x-axis plus the partial derivative of f with respect to y in the direction of y-axis. It's a directional vector. So think about it this way. Recall that when you have the dot product between two vectors, if you have two vectors like AB dot CD, the dot product between them is actually AC plus BD. So here you have A, and here you have your B, and here you have your C, and here you have your D. So you can rewrite this as the dot product between two vectors, I and J. There you go. So this is how we define this. Recall that I is unit vector 1 and 0, and J is unit vector 0 and 1. The dot product between two vectors is actually give you the gradient function. So now think about your directional derivative. The directional derivative of function f in the direction of vector u at the point like x sub 0, y sub 0 is defined as, very well, here you have f of x evaluated at point x sub 0, y sub 0. You multiply that by a plus f of y evaluated at x sub 0, y sub 0 times b. And remember that if you have polar coordinates, we can use cosine and sine. Note that a and b is a unit vector. A comma. So what's the connection between directional derivative and actually the gradient of a function? What are those relations. Here, note that we have f of x, f of y, and ab, we have plus sign. And remember that you know about the dot product. So this guy can be written as the directional derivative of the function at points x of 0, y sub 0 in the direction of u is actually the dot product between fx, fy, and a and b. Very well. So, what do you see here? Think about it. Very well. Okay, so let page 4. Let f of x and y be a differentiable function. And u, for example, is given as a function a comma b, and it's a unit vector. Then we can write the directional derivative of function f of x and y as the gradient of the function dot vector u. So note that, guys, directional derivative is always a number. So here you have a number. It's either positive, it might be negative, it might be 0. It shows the rate of change of the function. Rate of change of the function is a constant. It's a number. It's not a vector. It's just a number, not a vector. Gradient of f, it is a vector. So you're allowed to perform dot product between two vectors. The dot product between two vectors actually give you another number, not a vector. So vector 1, vector 2, it's not a cross product. Do not confuse that with cross product. It's a dot product between two vectors. The outcome is always a number. So one important note for you. Note the maximum value of the directional derivative duf is actually equal to the gradient of f, and it occurs when u is in the direction of gradient of f. One other important note for you is the gradient of f is always orthogonal or perpendicular to the level curves or level surfaces. Note the gradient of f is always orthogonal or perpendicular to the level curve, or if you're working with functions in free variables or level surfaces of function. So if the question says find the direction in which your directional derivative is maximum, you have to find the gradient of the function, find a vector which is in the direction of your gradient, and make sure that vector is a unit vector. One example and two checkpoints for you. So example 1 says, it says let function f be equals to sine x plus e to xy, then find the gradient of function f. What is that vector function? And checkpoint 1. This is checkpoint 1 on page 3. It says find the directional derivative. Find the directional derivative of a function f of x and y equals to x squared y cubed minus 4y at the point 2 and negative 1 in the direction of v equals to 2 and 5. Be careful here. Is that a unit vector? If it's not a unit vector, you have to write it in the form that it actually gives you a unit vector. Rescale it. Okay, gradient of f. So here we need to find the partial derivative of f with respect to x, partial derivative of f with respect to y. So the gradient of f, nabla f, is equal to, so the first component is cosine x plus, so here you have x e raised to xy, and we have to apply chain rule. So we get y e to xy, comma, then you have to take the derivative with respect to y. This is going to be 0 with respect to y. You get x e to xy. So as you see, we're getting back to Calc 1a using differentiation and chain rule. So for this guy, I use chain rule. For checkpoint on page 3, you might say, hey, I want to use what I learned at the beginning of this lecture. You can also use that, or you can say that, hey, since I learned about gradient of function f, nabla f, I'm going to apply that. So we learned that the directional derivative function f at point x sub 0, y sub 0, in the direction of u is equal to, so here you can just find the gradient of function f and then dot product with your u. Remember that we use u to emphasize on the fact that u is just a unit vector. Take a look at your v. The magnitude of v, the norm of v is equal to square root of 2 squared 4, 5 squared is 25. So you get square root of 29, which is not equal to 1. So unfortunately, v is not a unit vector. So we have to divide the coordinates of V by its magnitude to actually get a unit vector. This is equal to V divided by the magnitude of V. This is a unit vector. The first coordinate is actually 2 divided by square root of 29 and 5 divided by square root of 29. This is the vector, unit vector that you're going to use. So we're happy about this. We're sad because the length of the vector wasn't 1, so it wasn't a unit vector. We have to rescale the vector into getting a unit vector. Okay, so I'm going to continue that here. The gradient of function f is equal to, with respect to x and with respect to y. So nabla f is equal to, you get 2x y cubed, comma, it doesn't have any xness, but the derivative is equal to 0. Now we're taking the derivative with respect to y, we get 3x squared y squared minus 4. Very well. So of course you have to calculate the gradient of function. You plug in 2, you plug in -1, so the gradient of f at point 2, -1 is equal to 2 times 2, -1 to the third, comma, 3 times 2 squared, -1 squared, minus 4. So the gradient of function f at point 2, -1 is equal to, so let's do the calculation. Here we get -4, comma. So you have 12 minus 4, which is 8. So as you can see, the outcome is a vector, not a point. This is a vector. So the directional derivative of the function in the direction of vector u at point 2, -1 is equal to, the gradient of the function is -4 and 8, -4 and 8, and the unit vector that you have is 2 over square root of 29, comma, 5 over square root of 29. So let me just erase this happy face. I need a little bit of space. This is equal to, so we multiply the first coordinates, -8 over square root of 29. Multiply these two, plus 40 divided by square root of 29. Here, if you do the subtraction, you get 32 divided by square root of 29. We can rationalize this by multiplying that by square root of 29, square root of divided by square root of 29, or you can use your calculator, actually find this positive number. Okay, the last checkpoint that we have is on the last page. Very well. Our last checkpoint says, very well, here you have the function f of x and y equals to x e to y. Question says, find the rate of the change of the function. Find the rate of change of f at point, of course, we need the points 2 and 0 in the direction of. So in the direction of, we need the direction. In the direction from that point to another point like Q, a half and 2. So let us call it P. That's P. From that point P to the second point Q, B. In what direction does f has the maximum rate of change? So now question says, find the direction. In what direction f has the maximum rate of change? And see, what's the maximum rate of change? Now that we found the direction, what is that value? What is the maximum value of f? Okay, very well. So first, we need to find the direction. What is the direction? The direction is actually direction, or your v is actually, you have a half minus 2. So since we are working with a vector, let us use the vector symbol, a half minus 2, comma 2 minus 3. So connecting 2 points, P, Q. So your direction is equal to negative 3/2 and 2. Now you have to stop. Is this a unit vector? So we have to find the magnitude of v, which is square root of 9/4 plus 4. So if you take common denominator between these two, you get 9/4 plus 16/4. Here you get magnitude of v equals to square root of 25/4, or 5/2, which is not 1. So you have to rescale your vector by dividing the components by the magnitude or norm of your vector. So u is equal to vector v divided by its magnitude, which is equal to, so here you have 3/2, negative 3/2, divided by 5/2, then cancel out 2 and 2, comma, the second coordinate is 2, so divided by 5/2. And cancel out 2 and 2, so unit vector is now negative 3/5 and 4/5. So we are still on part A. We just found our unit vector. Okay, to make it easier, I'm going to find the gradient, which is a vector function first. So the gradient or vector function is equal to f of x, f of y, which is equal to, so f of x is just going to be e to the y, and f of y is x e to y. Very well. So my gradient at the point, at the given point, so the given point is 2 and 0. 2 and 0 gives me, so here I have e to 0, comma, 2 times e to 0, which is 1 and 2. This is my direction. What direction? This is the direction. It's a vector. Now I'm going to use what I learned in part B to answer part A. Why is that? Because the directional derivative of the function in the direction of u at the point x sub 0, y sub 0 is gradient f at that point times x sub 0, y sub 0, dot product to your u. So this is equal to, I have 1 and 2, dot product u negative 3/5 and 4/5. Okay, so I'm going to erase this part. I need more space. So here you get 2 and 0 equals to, here you have negative 3/5 plus 8/5, 5/5, or the directional derivative, rate of change of the function in the direction of, if 3/5, and just double checking my product, is equal to 1. And finally, last part, what is the maximum value of f? It's going to be equals to the magnitude of your gradient. So here we can find the magnitude of the gradient. The maximum value of f is equal to square root of 1 squared plus 2 squared, which is 4. 1 plus 4, or square root of 5. Guys, this is the maximum rate of change of f. Rate of change of your function. So let me just fix that. Maximum rate of change of function f, square root of 5.
Professor?